doing today? All right, sweet. Hello, my name is Steve, as we've probably gathered. And I'm an instructor at the Turing School of Software and Design out in Denver, Colorado. What is that? Woo, right? That is a 7-month developer training program where we take people who don't know how to develop web applications, and we hopefully show them how to develop web applications over the course of that 7 months. So if you're interested in mentoring people who want to become developers, please come talk to me. If you would like to hire like 6, 7, 12 developers, also come talk to me after this. I've got cards and all that other fun stuff. Other kind of like administrivia is that we're starting a NodeBots Colorado meetup on June 3rd. So if you are in the Denver Boulder region, come visit and hang out with us. Everything you're going to see today lives in a little README file on this repo, so you can play along. If you start playing with it while I'm talking, this is an audio talk, and I'll know. Right, so maybe you wait until lunchtime. But everything is there along with the slides and everything else. So as you probably gathered from the title of this talk, either A, you're in the wrong room, or B, you're here to hear a little bit about making music with a web browser. And so I have a little secret for you, and I guess I'll just kind of get this out of the way now, is that, as it turns out, somebody put a synthesizer into your web browser. It's true. So what does that mean? It takes the form of this fun thing called the Web Audio API, which Sam just kind of introduced us to a little bit, and I'm going to go in a little more detail with. And how do we use this Web Audio API? That's a great question. I'm glad that you asked it. It starts with some context. So if you've ever worked with like HTML5 canvas or anything along those lines, you're familiar with this idea of like a context. It's like the canvas that you're drawing on. In this case, it's the audio graph that you're working with. And in most cases, there is one audio context per page. So basically, you create one, you spin it up, and you start to hook together your different audio nodes. How do we do that? That is a great question as well. Basically, there is a built-in in the browser called audio context. There's a little bit of vendor prefix silliness going on with Safari. So in order to support Safari, we do this little quick trick on line 1 and 2 here where we'll say, hey, give me your audio context. Oh, you don't have that? Well, I'll take your WebKit audio context. Either way, and we'll do a little tomfoolery to get the right one, and then we can basically instantiate it. And now we have an audio context that we can play around with and use. And what is involved in audio context? Well, we need some way to get that audio out of our browser, right? So we have this thing called a destination. And the metaphor I'm going to use, if you've ever played guitar, it's like your amplifier. It's the thing that you're plugging everything else into. Technically speaking, it's like the operating systems, audio, whatever, right? It's an amplifier. It's your computer speakers, it's your earbuds, it's whatever. We also need some kind of sound source. And we connect that sound source to our destination, and we can make sound. The other cool thing is that we can put a whole bunch of stuff in the middle, right? Like effect pedals. So if you were playing guitar, it would be a wah-wah pedal, or a delay pedal, or a chorus pedal, right? We can take other audio nodes, take whatever the input source is, do some processing on it, and then send that kind of processed version of our audio to the destination and get to use it as well. So let's start by talking about the first piece of this. We want to get some sound out of the browser, so we're going to need to set up that audio context destination. And that is also pretty easy to do. That context that we created in the last little code sample, it's got a bunch of properties and methods on it. One of those is destination, and that is a representation of your audio context destination. It is your amplifier. It is what you're going to plug other stuff into and where sound is going to come out. So we've got a destination, and now we need some kind of audio source. We've got a bunch of options. We could load in some kind of sound file. That'd be cool. We could take something from the user's microphone and analyze it and process it along those lines. Or we can generate our own tones. Now, we're talking about making music with the browser, right? So the first two are kind of off the table. We don't want to take a pre-recorded music and play it. That's been done, right? It was MIDI files in the 90s. It was on my GeoCities page. I'm not embarrassed of that at all. We don't want to just record other sounds and be able to analyze it. We want to actually make sounds. So our hero in this story today is going to be the oscillator, which you got a little bit of an introduction to in the last talk. And an oscillator basically creates a sound wave. And a sound wave is this kind of like vibration in the air that your ear makes some sense out of and turns into a given tone. And there's some distance in between each of the waves and the amplitude, which is how high the peaks are and how deep the valleys are, right? Which for our purposes today is basically the volume. How do we create an oscillator? Again, we've got some methods on that context that we created before, and all we have to do is call create oscillator, and we have created an oscillator. And that's great. Now we have an oscillator, and we've got a destination. What we need to do next is connect the two of them. We need to take our keytar in this case, and we need to plug it into our amp in order to get any sound out of it. So we've got a few more methods. Now we've got a method on that oscillator, and we can connect it to the context destination. So we're plugging our keytar into our amp, and we're almost ready to rock and roll. Almost. Because the other thing we need to do is actually, like hit some keys on that keytar in order to play anything. So the other thing we need to do is start our oscillator, turn it on, and have it begin to create some sounds for us. And so that's pretty easy to do as well. How do we start an oscillator? We call start on it. You might be wondering, what is this 0? That is when you want it to start, how far in the future you want it to start. In this case, we want it to start right now. Firefox and Chrome, totally okay with you omitting this, and let's just start it immediately. Safari, not okay with this. So we can put in a 0 saying, hey, I want to start this oscillator, and I want to start it right now. And that's great. Like, you probably messed up what frequency you want. If you're like me, you're blowing out your eardrums right now with a super high-pitched frequency. Congratulations. And now you probably want to stop it. Surprise, the method is called stop. Here's where it gets tricky. All right, I have done blowing out my eardrums. I want to adjust the frequency, and I want to start the oscillator again. Not going to happen. Right? Here's the kind of gotcha on that. Once you stop an oscillator, you cannot restart it. Game over. You have to get rid of it and get a new one. So you might say to yourself, all right, yeah, I'll just generate another one, no big deal. The other thing you want to make sure that you do is disconnect that oscillator that you had so that it can get garbage collected. If you don't disconnect it, the context destination still has a reference to it. It's still hanging around memory. You get a little out of control and start doing that too much. Congratulations, you have a memory leak. Don't have a memory leak. Disconnect your oscillators when you're done. It's the responsible thing to do. All right. So now it's gotten garbage collected. We can bring in a new one. And here it is. The other thing we talked about before is that we can connect stuff in the middle. So you might say, I don't want to keep creating and destroying oscillators. That seems reckless. I'm not interested in doing that. It's actually pretty efficient. It's not a big deal. But it makes me feel a little dirty. So the other option is to plug in our sound source into some kind of intermediary node that will process that sound. And in this case, if we use the gain node, we can basically turn up and down the amplitude, which for our purposes is the volume. So we can turn the volume down to 0, and yeah, the oscillator's still running, but none of that sound is getting to the destination, which means for all intents and purposes, the thing is stopped. That's it. And when we're ready to hear from it again, we can turn the gain up to 1, which is the kind of the default setting, and all of the sound will continue to travel through. So we kind of get to like mimic the idea that we're turning an oscillator on and off, but really we're just adjusting intermediary gain node instead. How do we do that? There should be no surprises here. Context has a few other methods for generating all the other intermediary nodes that we might need. In this case, we'll create a gain node. And we can then hook up our keytar to our gain node. So we'll connect the oscillator to the gain node. Then we'll hook the gain node up to our destination. And now we can start the oscillator, and we can just adjust the volume to kind of give the illusion that we're turning it off and on, but in fact, we're just simply adjusting, again, an intermediary node. So again, we notice that we're talking about the oscillator. Oscillator's got a bunch of other properties to it. It's what frequency what should be the bandwidth of those waves, right? How close together or far apart should they be? By default, we get an oscillator that is at 440. But we can adjust it down to 220. We can adjust it up to like 8,000. Don't do that if you're wearing headphones, again. I don't know if there was malls in the UK a few years ago would play super high-pitched tones, because as you get older, you can't hear those. So like it would be for the sole purpose of scaring away teenagers. right? So there's a use for this in your practical everyday life when you want teenagers to go away. Create an oscillator at a super high frequency and turn it on. You might also scare away your dog and cat. That could be a bonus, depending on how you feel about them at that moment. So we have a bunch of different types of waves, right? And this is basically the shape of the wave. And we get a few out of the box by default. A sine wave is this kind of nice, curvy, happy wave. It sounds pretty pleasant to the ears. A square wave gets its name from looking like squares. A triangle wave gets its name from looking like triangles. And a sawtooth looks like a saw, right? There's not like a lot of like heavy like vocabulary here. It's like, hey, that's what that wave looks like. And you can use any of those. If you want, you can also create your own custom waveforms that are different than those, but those are kind of the default traditional like synthesizer sound waves that we've had available since like the 70s. And we can basically, Oscillator has a property on it where we can change it to whatever type of wave that we want. So let's actually take a look at this. We're going to look at a little example where we can kind of create an oscillator. There we go. I can adjust the gain here. And so this is a sine wave, and we could change the frequency. And you can see as the frequency increases, then in that case, the kind of pitch to our ears sounds higher. We can also, I'm going to go back down to 220 for everyone's benefit, because I care. And we can try out a square wave. You see, if I had kept that at 440, you'd all be regretting it. Sawtooth, and a triangle. So the shape of the wave has different tonal properties to our ears, and we can kind of change one. For the rest of this talk, we're going to be going with the nice sine wave, because it's probably the most pleasant. Cool. So at this point, we now know how to make sound, and that's super cool. But sound is necessary, but it's not sufficient for making music, right? So it's called the Web Audio API, not the Web Music API. It's going to help us make some sound, but it's on us to turn that sound into some music. So we're going to need to know a few things about music in order to get this working. So we talked a little bit about the default frequency of an oscillator is 440. 440, if you've ever seen like one of those tuning forks, that is A4, and it's kind of like where we base most of our just general tones on most Western musical instruments. So we got 440. If we were to double that frequency to 880, conveniently, we would get A5, which is an A note but an octave higher. And if we were to have 440 to that 220 we had before, we would have A, but an octave lower. I don't know if you know this, but there are more notes than just A. So we have these things called semitones, and it's the 12 units in between two octaves. And again, it's simply a Western music thing. It's not like a physics law or anything, but we have decided that these are the tones that sound reasonably pleasant to our ears. And some of them have some basis in actual physics. If you take a guitar string and put your finger in the middle and play a harmonic of the middle of the string, that is usually one octave higher. If you put it a third of the way through, you'll get a fifth, so on and so forth. So you get some of the basic ones, and then we kind of filled in the gaps. So you might say to yourself, all right, well, if I want to get the rest of these notes, I'll use math. And that seems really reasonable, because at first glance, it works, right? So this is simply, we've got A at 440. If we look at A an octave up, it's 880, and if we divide by 1/12 steps each way, we get there. No big deal. It sounds great. Unfortunately, it only works in one key. Right? If you were to start at C, you can see almost immediately the notes don't match up. So if you were to use this kind of mathematical approach, you could create an instrument that only sounds good in one key. And that's, it's called a harmonica. Right? And you buy a whole bunch of them, and you never learn how to play them, and that's, kind of how it works. So the first thing I tried to do was all right, I'm smart, reasonably. I can figure this out. So I'll come up with an algorithm that'll work. Unfortunately, this is a problem that humans have been working on for thousands of years, and I was not able to figure out on one Red Bull-fueled afternoon. However, it occurred to me that, you know what I'll do? I'll just steal an approach that already works. We have figured this out. This is a solved problem, right? So that going by units of 1/12 is equal temperament. The other approach is to use this thing called just intonation, which is a bunch of ratios that are compromises between all the keys. So no, it is not perfect, right, in like the kind of like physical sense of, and in the way of like equal temperament, but it is reasonably good in every key, but not perfectly accurate in any of them. Right? So we could steal something from the piano. So now I just needed a way to get from piano tones and piano frequencies and just steal a little cheat sheet from that and be able to use it. And as I was doing more and more projects, doing this each time and just keeping a giant hash table in a file and like trying to reference it was getting obnoxious. So when you have a need and a possible solution and you have a cute name for a project, you have an open source library. This is a little library called Octavian, and basically what it does is you can hand it just a general note. And what it'll do is it'll give you the frequency. It'll also give you all other things that you might need to use about it, like what key on the piano it is. And all it does is basically reference a lookup table of like this note on the piano, this would be this frequency. The other fun thing that it does is it lets you actually do the different intervals between notes. So like a major chord is a root note, it's a major third and a perfect fifth. A minor chord is a root note, it's a minor third and a perfect fifth. So you can kind of like reason about these notes and get everything you need along the way. All right, so now we can create sound. And the other thing we can do is we can reason about it in terms of music. Let's actually build a musical instrument. So this is a little example instrument called Audiophonic. And let's take a look. Adam? Adam's going, ladies and gentlemen, Adam Sontag is going to play us a song. All right, you ready?
All right. So this is he really oversold. What happened was I saw this last night, and then I figured out the beginning of the first song on the like second most recent Shins record. Then you have to go up. It's really hard without looking.
Yeah.
Actually, I'm just going to play the blues because that's what I have now. What great music.
Round of applause for Adam.
More like AJ's synthesizer.
So as you can see, we can hover over a bunch of notes, and it'll play tones. And if we press a key, it'll actually like activate that tone. So we've created a musical instrument. Now, all right, that's great. How exactly did we do that? So the trick here is we basically spun up a bunch of oscillators and hooked them all up to gain nodes. And on different events, we'll simply turn one of those on and off. So when a key gets pressed, we'll listen for a key down event. When that key down event happens, what we'll do is we'll say, all right, I have this like synthesizer object, it'll like, get me an oscillator for C3. And it will go ahead and look up, do I have one in this notes hash? No, if I don't have one, what it'll do is go and put one in there for me. There we are, I'm caught up. And then return it out. Now, a real synthesizer usually has like 3 oscillators that it's adjusting the frequencies on and turning on and off, but I've got 16 gigs of RAM, and I'm going to treat myself to like 80 oscillators, because I can do that, right? So I'm just going to keep them all in a hash, and if I have one, great, use it. If I don't have one, make it, put it in the table, and then use it as well. And you might say, like, what is this new oscillator thing? It's just a little abstraction, and all it does is like it creates an oscillator and a gain node, it sets some default values on them, in this case the frequency that I want an oscillator for. It'll hook them up together, it'll start it, return it out to me, and I've got these start and stop methods that are not actually start and stop methods on the oscillator, but on that gain node. So for me, I feel like I'm working with an oscillator, but there's just a few more things happening in the middle. So then we can say, all right, if we hit the button that's bound to C3, get me an oscillator for C3, start it, and when they do a Keyup event, we'll simply send that off and we'll stop that oscillator. And that's all we need to do to create a very small synthesizer. Nothing like saying that in front of 600 people. So that's cool, but that's only like, why wouldn't you just buy a keyboard at that point? right? Why did you need to do all this? I mean, it's fun, totally. You can share it with your friends and they'll start using it at night and they agree to come up on stage and play a song in front of everyone. That's awesome. But like, why else would we want to use something like this? Well, the other really kind of interesting part is that somebody put a web browser in your synthesizer, right? That's not the only API that's available in the browser. So the fun comes in when we start mixing and matching different APIs. So one example is we can mix the web audio API with the getUserMedia API. My favorite slide coming up. So this little app called Theremin. Are you guys all familiar with what a theremin is? It's like the thing. It's making the spooky like 60s like UFO music, and you like lift your hands over some things. I thought, hey, it would be really cool if I could do that with my face. So what we'll do, I can't actually see myself here. Hold on. In fairness, most of the hard work there is being done by the head tracking software. So it detects your face, and when you move your face, it emits a face tracking event, right, which has a whole bunch of properties on it. I really only care about 2 of them right now. You might care about other ones, but height and the x value. The x is the horizontal, where am I in this direction or that direction, and the height is how close or how far I am. And I'll take those 2 properties, and I will do some simple math to make sure that they're reasonable frequencies and gain amounts. And then I'll take my oscillator and my gain value, and I will adjust them accordingly. And that's really all there is to it. I mean, there's also the entire face tracking library, but that's somebody else's problem. And then lastly, I will bind myself to that event and update stuff along those lines. Okay, so now we're seeing the real power here is when we can mix and match other APIs. What about WebSockets? All right, so you might say, cool, we can have an instrument where a bunch of people can play in real time together. There is some latency, so you don't want a bunch of people moving their heads together or something, like synchronized head movements. Or maybe even playing keyboard tones, because there's going to be some latency. And the other part about music that I never had was rhythm. So that's going to be an issue with the latency thing. But we can kind of address that by using what's called a step sequencer. Right, a step sequencer, we've got 16 quarter notes, which I have 0 indexed because this is a JavaScript conference. And they are quarter notes, and we'll kind of step through each and every one of those. And then the rows are a bunch of musical notes. In this case, I have only chosen C, E, G, and A, because it is very difficult for you to make a melody that sounds bad with that. I mean, you could probably do it. I believe in you. But it makes it when you have multiple people playing. So now what we can do is anytime somebody activates a square on the grid, we send that over WebSockets to a little express socket.io server that will then take that sequence, match it up with all the other ones it has, and push it out to all the other connected clients. And what we'll do then is when it gets to the client, we'll take all the sequences, and for the user sequence, we'll make those the bright yellow. For everyone else, we'll make them this pale color. We'll render all the other sequences below. But we'll then combine them all to one sequence that'll get played out. So it'll be everyone's music together. So let's actually take it for a spin. Beep. Next slide. Now you know what's coming next. All right. There's my face again. All right, so here we've got a sequencer, and I happen to have an iPad over here to be my other set of ears. So I can begin to unmute, and I'll start playing a bass line. This is so hard when I can't see. Yeah, I was off there. Huh. This is fun to watch me do, right? All right, so I've got a bass line going. Just so you believe me, iPad. So I can start playing a melody here. I don't know what I'm doing, by the way. playing on the iPad. Here's the kind of bass line that I put down in my browser, and they're all being connected. Ideally, you could have tens, 20s, hundreds of people kind of creating music together around the world as well. And there's a link to this in the repo that I posted in the beginning, I'll have at the end. So I totally encourage you during lunch, fire it up and let's have a JSConf song. Right? It's only going to be 4 measures long and made out of 4 different notes, but whatever. Mute. All right. So that's cool, but so far we've also been a little bit limited by what we've been able to do on the screen. So we've kind of had to either bound stuff to the keyboard, which is kind of cool, but also kind of difficult because that's not a musical instrument. And where we've been able to click on different things. As we know, JavaScript runs on the client, it runs on the server, and it also runs on hardware, which means we can begin to build our own musical instruments. Right? I've got a very small example we're going to switch to in a moment, but it means you can build like a Nintendo Power Glove. There's an 80s reference, by the way. A Nintendo Power Glove where every pinch of the fingers started to play a different note. It means you can use all the other sensors that's on available for Arduino and begin to create hardware musical instruments programmed in JavaScript that work with the web audio API in the browser. So this is a really clear diagram of what I've got going on here, and I'll explain this. But basically, we got some buttons, and we've got a little potentiometer. And whenever we hit one of the buttons, that'll send a signal to Johnny 5. Johnny 5 will then has an Express and WebSocket I/O server running alongside of it, which is incredibly easy to do, by the way. And we'll send that data over WebSocket to the browser, and the browser will then update and start playing the right tone based on the button that we hit. So here we can say, all right, I'm going to listen for pins 2, 4, 6, and 8. I'm just going to keep them in this quick little object over here. I'm going to say, when the button is down, we'll send whatever key that was, and whatever button that was, and we'll send that as true. When the button is up, we'll send one saying it's false. Basically, the status of the buttons on my board, I'm sending them out to the browser. And then the potentiometer is going to, as we turn it, go through all of the notes between C3 and C5. All right, so let's check out the demo. There's my mouse. Cool. So basically, at this point, now that we can build our own hardware that creates music in the browser with JavaScript, there's very limitless possibilities. And so the moral of the story is that music is pretty awesome. I think we can all agree on that. The web, also pretty awesome. Music and the web together are like ice cream and cookie dough. Each individually awesome, but exponentially more awesome when put together. And we only kind of scratched the surface. There's a bunch of other really cool APIs. There's the Gamepad API. There is WebRTC, so you could theoretically create multi-phase theremin. There is the gyroscope accelerometer API in mobile devices. There's the device orientation API. And there's also mixing and matching more of the different examples that we already went over. Right? So there's a bunch of limitless possibilities for you to create musical instruments that have never existed before. So I kind of want to encourage you to do that. On the page that has the links to everything, if you make something really cool, please send me a pull request, and we'll put a link below. And let's collect all the really cool musical instruments that you make in the next days, weeks, and months. And with that, thank you very much.